This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today, we're delving into a research paper detailing a novel air-ground robotic collaboration system for executing missions specified in natural language even in unknown environments. The system dynamically adapts to changing mission parameters. What are the key challenges this system addresses that existing approaches struggle with?
Existing systems often rely on predefined tasks and fixed semantics, limiting their adaptability to real-world scenarios. They also frequently assume near-perfect environment knowledge and continuous communication, which are unrealistic in many applications. Our system tackles these limitations by enabling language-driven mission specification, dynamic semantic configuration, and robust strategies for handling intermittent communication.
The paper mentions the use of large language models, LLMs. How crucial are LLMs to the system's functionality, and what specific role do they play in mission planning and execution?
LLMs are central to the system's ability to interpret natural language mission specifications. They act as a planner, reasoning over semantic metrics maps built online by both the aerial and ground robots. The LLM infers mission-relevant semantics, generates subtasks, and coordinates actions between the UAV and UGV, adapting to changes in the mission specification on the fly.
The system uses a decentralized semantic mapping approach. Can you elaborate on the architecture and how information is shared between the UAV and UGV, considering the potential for intermittent communication?
The system employs a decentralized, compact semantic mapping approach where both the UAV and UGV build and share observations opportunistically. The UAV, which is high vantage point, creates an initial semantic metric map, including traversable regions and objects of interest. This map is incrementally transmitted to the UGV via a gossip-based communication framework, MOA, that tolerates intermittent connectivity. The UGV then augments this map with its own observations.
The paper highlights the use of opportunistic communication. How does this approach differ from traditional communication strategies in multi-robot systems, and what are its advantages and disadvantages in this context?
Traditional approaches often assume continuous communication, which is impractical in large-scale, unstructured environments. Opportunistic communication, as implemented with MoCA, allows robots to operate independently when communication is unavailable, leveraging communication opportunities to share information and coordinate actions. The advantage is increased robustness and scalability, but it requires sophisticated strategies to handle potential communication gaps and ensure mission success.
The system uses a semantic topological graph representation. Why was this chosen over other map representations, and how does it facilitate planning and decision-making within the LLM-enabled planner?
The semantic topological graph provides a structured representation that captures both the spatial relationships, topology, and semantic information, objects, regions, traversability of the environment. This structured format is crucial for efficient communication between robots and for enabling the LLM to reason effectively about the environment and plan actions. Other representations might lack the necessary structure or be too computationally expensive for real-time operation.
The paper mentions several experiments conducted in various environments. What were the key findings from these experiments, and how well did the system perform in terms of mission success rate, robustness, and scalability?
Experiments in urban and rural environments involving kilometer-scale navigation demonstrated the system's ability to successfully complete 7 different natural language mission specifications. The success rate was high, showcasing the system's robustness to environmental variations and intermittent communication. The use of compact map representations and opportunistic communication contributed to the system's scalability. However, challenges remain in robust traversability estimation and handling highly dynamic environments.
The paper discusses limitations, particularly concerning traversability estimation. What were the main challenges encountered in this area, and what are potential solutions for future work?
Accurate traversability estimation proved to be a significant bottleneck. The UGV struggled with identifying small obstacles and false positives in the UAV-generated map. Future work could focus on improving traversability estimation techniques, potentially integrating robot-specific sensor data, and more sophisticated perception models. Also, incorporating more robust local planning algorithms could help mitigate the impact of minor localization errors or map inaccuracies.
The reliance on an external LLM API is mentioned as a limitation. What are the implications of this, and how could future iterations of the system address this dependency?
The reliance on an external LLM API introduces a dependency on a robust communication infrastructure and increases latency. Future work could explore integrating onboard LLMs to reduce this dependency and improve real-time performance. This would require careful consideration of computational constraints and the trade-off between model size and performance.
The paper suggests several avenues for future research, including improvements to traversability estimation and the use of onboard LLMs. Are there other promising directions for future development of this air-ground collaboration system?
Yes, several other areas warrant further investigation. One is enhancing the system's ability to handle more complex and ambiguous natural language instructions. Another is improving the coordination between multiple ground robots, enabling more complex collaborative tasks. Finally, exploring different sensor modalities and data fusion techniques could further enhance the system's perception capabilities and robustness.
The system demonstrated the ability to handle dynamic mission specifications. Can you provide a specific example of how the system adapted to a change in the mission parameters during an experiment?
In one experiment, the user initially tasked the UGD with inspecting a black vehicle at the end of a driveway. However, the vehicle was actually located at the beginning. The system, using active perception and the LLM, identified the vehicle at the beginning, queried its color, and corrected the mission accordingly, demonstrating its ability to adapt to unexpected situations and resolve ambiguities.
The paper mentions the use of grounded SAM-2 for object detection. Why was this model chosen, and what are its advantages in the context of this air-ground collaboration system?
Grounded SAM-2 was selected for its zero-shot open-set performance, meaning it can detect objects without requiring pre-training on specific object classes. This is crucial for handling the diverse and unpredictable objects encountered in real-world environments. Its ability to perform accurate segmentation also aids in precise object localization.
The system uses a receding horizon planning approach. How does this contribute to the system's ability to handle dynamic environments and unexpected events?
Receding horizon planning allows the system to continuously replan based on new observations and changes in the environment. This is crucial for handling dynamic situations, such as the appearance of unexpected obstacles or changes in the mission specification. By replanning at each step, the system can adapt to these changes and maintain its progress towards the mission goals.
The paper mentions the use of a vision language model, VLM. What is the role of the VLM in enriching the semantic information available to the planner?
The VLM enhances the semantic understanding of the environment by providing detailed descriptions of detected objects and scenes. This richer semantic information allows the LLM-enabled planner to make more informed decisions, improving the accuracy and robustness of the planning process. For example, the VLM might provide a detailed description of an object, including its color, size, and condition, which the planner can use to make more accurate assessments.
The system incorporates a plan validation module. What is the purpose of this module, and how does it contribute to the overall robustness and reliability of the system?
The plan validation module acts as a safeguard against potential errors generated by the LLM. It checks the feasibility and consistency of the LLM-generated plans, ensuring they are syntactically correct and physically realizable. This helps prevent the execution of unsafe or illogical plans, enhancing the overall robustness and reliability of the system.
The paper describes the use of a custom GNSS/INS system for accurate pose estimation. Why is accurate pose estimation so critical for the system, and what are the challenges in achieving it, particularly in the context of aerial robotics?
Accurate pose estimation is crucial for correctly localizing objects in the environment and building accurate maps. In aerial robotics, challenges include the effects of wind, GPS signal loss, and sensor noise. The custom GNSS/INS system addresses these challenges by fusing data from multiple sensors to provide a robust and accurate pose estimate.
The system demonstrates a human-in-the-loop capability. How does this human interaction enhance the system's performance and adaptability?
Human-in-the-loop interaction allows for dynamic retasking and provides valuable feedback to the system. The human operator can provide additional instructions, clarify ambiguities, and intervene in case of unexpected events. This interaction significantly enhances the system's adaptability and robustness in complex and unpredictable environments.
The paper mentions the use of a system prompt to configure the pre-trained LLM. Can you elaborate on the components of this system prompt and how it shapes the LLM's behavior?
The system prompt provides the LLM with essential context and instructions. It includes a role description, defining the LLM's role as a planner, a mapping interface, specifying how the LLM interacts with the semantic graph, and a description of the behavior library, defining the actions the LLM can take. This carefully crafted prompt guides the LLM's behavior and ensures it generates appropriate and consistent plans.
The experiments involved both single UGV and air-ground teaming scenarios. How did the performance of the air-ground teaming system compare to the single UGV baseline, and what insights does this comparison offer?
The air-ground teaming system significantly outperformed the single UGV baseline, particularly in large-scale exploration tasks. The UAV-generated prior map provided valuable information, enabling the UGV to navigate more efficiently and complete missions that were impossible for the single UGV system. This highlights the synergistic benefits of air-ground collaboration in challenging environments.
The paper concludes by outlining several open challenges and future research directions. What are some of the most significant challenges that remain to be addressed in the development of robust and scalable air-ground robotic collaboration systems?
Significant challenges remain in improving the robustness of traversability estimation, handling highly dynamic environments, and reducing the reliance on external LLM APIs. Further research is needed to develop more sophisticated perception models, robust planning algorithms, and efficient onboard computation for LLMs. Addressing these challenges will be crucial for realizing the full potential of air-ground robotic collaboration in real-world applications.
This has been a comprehensive discussion on the intricacies of this innovative air-ground robotic collaboration system. Thank you.